So today we'll discuss the remaining part of surface tension, right? So that is, I think you studied the previous parts well, because it will be useful here, right? When it comes to the remaining lessons, right? Just write the topic capillary rise, subtopic, right? Capillary rise and capillary rise and capillary fall. Capillary rise and capillary fall, right? You might have heard that about capillary rise. So that you know that the water is sent through the trunks of a tree via capillary rise, right? So that is one of the factor that water carries up to a tree. So this phenomena. So the reason for the capillary rise is actually surface tension, right? So that we will be discussing here. First, I will give you the note, then we'll discuss that, right? Write down when a capillary tube. Write down when a capillary tube is immersed in a liquid like water with this symbol, right? Phi. Phi means contact angle, okay? Phi, comma, an acute angle. Phi, so this is acute angle. Acute angle, comma, it causes a capillary rise. It causes a capillary rise. Full stop. When it is immersed in mercury, when it is immersed in mercury, where this one pi is an obtuse pi is an obtuse angle, it causes a capillary fall. It causes a capillary fall. Okay? Full stop. To the same line, right? When phi equals 90 degrees. Phi equals 90 degrees. That is contact angle, right? Equals 90 degrees. There is neither capillary rise, nor fall. No fall. Right? Okay. So this is three situations. So this is what happens, right? Really important. So there are three situations I have to discuss. One is you immerse a tube, uh, mostly a capillary tube. You know capillary tubes, right? Its internal radius is very thin. For other tube as well it happens, but for a capillary tube, there's a significant capillary rise. Okay, if the internal diameter is higher, capillary rise it is not that visible, right? Thinner the pipe, the more visible the capillary rise or fall. Okay, so usually we use to demonstrate capillary rise, we use a capillary tube, right? So let's say this is a cross section. Can see, right? Cross section of the capillary tube, somewhat enlarged, right? You immerse this vertically in a liquid. In this case, it is water. Then what happens? So according to hydrodynamics, we know that liquid should be at the same level, right? At the same level. But there is another force acting here. That is surface tension. So because of the surface tension, what happens? The water is attracted to the glass. So it is very attractive to the glass. Then there's a capillary rise, somewhat like this. This is totally because of surface tension, right? This is totally because of surface tension. According to hydrostatic, the liquid level should be at the same level, right? But here, surface tension is at work. So the surface tension forces are acting like this, upwards. You can see contact angle is like what? Here you have the contact angle, right? So you can see it is a acute angle. Contact angle, it is acute angle. So it is like this, let's say like a sack or something. When the meniscus gets this shape, contact angle is an acute angle. So it lifts the liquid column upwards. So the forces working here is surface tension forces. So that's what happens, right? So at the first case, it is water. Then at the second case, what happens? You immerse the capillary tube in mercury. So when you immerse it like this, contact angle has to be obtuse. So the meniscus would be like this. So you can see this tangent and this tangent angle is obtuse, right? So to which direction surface tension forces are working? Now it is working downwards, right? So the liquid level is pushed downwards inside the tube. Inside the tube. So whenever the liquid contacts with the glass, it has to create a obtuse angle. So this is not possible if there's a capillary rise. Now this is called capillary fall, right? So this is a capillary fall, this much of a capillary fall. This also is due to surface tension. So here capillary rise, capillary fall. So let's say you have a liquid, its contact angle is 90 degrees. Here the contact angle is less than 90, here the more than 90. Then you have a liquid with 90-degree contact angle. Now what happens? Liquid level, it it will be like this. It will be flat inside it. So there is neither capillary rise or fall in that case. See that? Because surface tension forces are acting perpendicular to the glass. Here it is acting downwards. Here it is acting upwards. It is so the surface tension forces always acts along this tangent, right? Here to this direction. So by applying a force, surface tension applied perpendicular to the tube, there cannot be a rise or a fall, right? I think you understood that. Okay, so this is the three cases. Take this down. Below the sentence, take this down. If you have any problem, let me know. Right. Below this, write down this sentence. When the tube is thinner, when the tube is thinner, when the tube is thinner, comma, higher the capillary rise or fall. Higher the capillary rise or fall. When the tube is thinner, comma, higher the capillary rise slash fall. Remember that, right? I will show you using equations as well. Let's say the radius, internal radius is small. So thinner the tube, higher the capillary rise, right? So that's how, even though the trees are very high, the surface tension contributes largely to carry water upwards, up to the leaves, right? Because they have like very minuscule tubes there. So what are they called? Capillary tubes or something, right? In water, sorry, in trees. Those tubes are actually, the radius is really minuscule. You can only see using like a microscope. So the capillary rise is going to be very large in like trees. Okay, below this write down subtopic. Below this write down deriving an expression for capillary rise, derive an expression for capillary rise using force equilibrium. Deriving an expression for capillary rise using force equilibrium. Right? Using force equilibrium. First, I'll talk about this when contact angle 0. So when the contact angle is 0, I'll explain this it first, right? So here what happens? So I'll draw the tube. So this is like water and glass, right? So let's say you know when the contact angle is 0, so this is the solid surface. If you draw a tangent to the meniscus, through the liquid, it also goes through the surface. So the contact angle is 0 here, right? So the surface tension forces are acting upwards like this. Okay. If you take a 3D shape of the meniscus, it is like this. Can you see that? It's like that, right? This is how the surface tension forces are acting. Right? Think like kind of like a sack. Around it, surface tension or forces are acting upwards. Okay? So these forces raise this liquid column. Understood? Then what can we do? So you have to find the total surface tension force. What is that? T times surface tension coefficient times length. Length is, this is a circle, right? So I'll just say length. It is equal to mg. Mg means weight of the water column. I mean, this rise amount, weight of the water column is equal to the force applied by the surface tension. So the water column is balanced. That water column is balanced by the surface tension forces once it rises, right? So this is T. What is length? Given that internal radius of the tube is simple r, you can say it should be 2 pi r, right? 2 pi r equals mass. So how do we find the mass of the water column? That is density times volume. Mass is density times volume. Let's say the density is rho. Then what is the volume of this water column? Let's say capillary rise is simple h. Capillary rise is simple h. So you can see this is a cylindrical shape, right? This is like a solid cylinder. So how do we find the volume of a solid cylinder? Pi r is squared, that's a top area, times h. Understood? Then from using that, you can get a somewhat of an equation. Pi cancels off. You can get rid of 1 of r. Then you have 2t. 1 r I cross multiply and take it to the other side. 2t divided by r equals, here h rho, there should be g as well, right? This g, h rho g. 2t divided by r equals h rho g. So if they ask capillarize, you just have to subject h. Just remember this form of the equation, right? When they ask a question, remember this form. 2t divided by r. So you know the terms, right? 2t internal radius, capillary rise, density of liquid. 2t divided by r equals h rho g. H rho g you already remember. Just remember that it is also equal to 2t over r when it comes to surface tension, right? So if they ask capillarize, you can subject h and find capillarize. Understood? Okay, quickly take this down. So when I draw margin, you need to remember that equation, right? Those are standard equations you can directly use. Okay? If you are done, thumbs up. Right. To practice this, I'll give you a question. Write down Q. Write down. Find the capillary rise. Find the capillary rise. Given that internal radius of the tube is 0.2 millimeters. 0.2 millimeters, comma, immersed in water. Immersed in water. Okay, try that question and send me the answer. That is easy, right? You can directly use this. You don't have to prove this again. You can directly use. You can use this 2t divided by r rho g. Then you just substitute. So what's the t value? You know that, right? For water and glass. That is 7.2 times 10 to the power minus 2, right? You can easily calculate that. Send the value, right? In the message. Quickly. Yeah, correct. 7.2. Let's see. Is it minus 3 or minus 2? This is 0.2, right? Yeah, this is 0.2. Yeah, so you get minus 2 meters, right? So when if you want, you can say it in centimeters. So it should be 7.2 centimeters, right? So when you have a 0.2 millimeter internal radius, you can see a 7.2 centimeter capillary rise. Yeah, correct. Minus 2. Then write. So at the first case I talked about when phi is equal to 0. Here I'll talk now. This is the second case when phi is an acute angle, right? Less than 90 degrees. Write down. Now you have a liquid. Meniscus is like this. It could be like this. Now it is not hemispherical, right? Contact angle is less than 90 degrees, not 0. So the surface tension forces are acting like this, not along the tube, along the tangent. Now tangent is like this. And if you draw that 3D image, it is not vertical. Surface tension forces are like this. Understood? Now these forces, these surface tension forces, balances out this much of a capillary rise, this much of a water column. Not water, it could be anything else. This amount of a liquid column is balanced by these forces. So how do we do the force equilibrium? So we know that weight of this water column is downwards. So we have to take the vertical components of surface tension forces. So we know that what is this angle? That this angle is contact angle, right? So this angle also should be phi. So what do we have here? T cos pi. So those are the vertical components of surface tension. T cos pi times length. What's the length? It is 2 pi r, right? 2 pi r is equal to weight of the water column. How did you write the weight? Density of the water column. Then volume of the water column. What is that? Phi r squared h. This is h, right? Times g. Okay. Then you can cancel off same ones. Then you get 2t cos pi divided by r equals h rho g. So if the contact angle is not 0, what's the only difference? For the previous one, it was 2t divided by r, right? Now it is 2t. There's a cos pi term. Cos contact angle. That's the only difference. Because you are taking the vertical component. Now you are taking the components, right? Okay, take it down. Remember in this form, right? It is easier. H rho g equals 2t divided by r. If there's a contact angle, 2t cos pi divided by r. Easy. If you are done, thumbs up. Right. So that's all about capillary rise, right? Capillary rise, I derived them using force equilibrium. So you should be able to derive that as well, right? It is not that complicated. and also remember the equation. So that is all required when it comes to capillary rise. There's another way to derive this. I'll explain that later. Before that, there's the another phenomena I'll explain. Write down the next topic. Pressure difference. This is pressure difference across a liquid drop. Pressure difference across a liquid drop. Pressure difference across a liquid drop. Right. So you have a liquid drop, right? Inside the liquid drop and outside the liquid drop. Let's say liquid drop in air, right? There's a liquid drop in air. If you think about the pressure inside the liquid drop and outside the liquid drop, there's a difference. That difference is due to surface tension, right? That difference is due to surface tension. So that is what we are going to talk about here, right? First, write down this sentence. Internal pressure of a liquid drop, internal pressure of a liquid drop in air or an air bubble in a liquid, air bubble in a liquid is higher than the external pressure of it, okay. Now listen. So here we have a liquid drop in air, surrounding it air, it is a liquid drop. Then we have air bubble. Inside it is air, outside it is liquid. Okay. Let's say internal pressure is P1, external pressure is P2. So here also we can take P1, external pressure P2. You have to remember this, that internal pressure is always greater than external pressure. Same case here, right? Sorry, P1. Take it down. P1 is greater than P2. Internal pressure is greater than external pressure. You need to remember that, right? I'll prove that, we can prove this, but first you have to remember this. This pressure difference is totally due to surface tension, right? Surface tension. If you neglect surface tension, then you can say pressures are the same, but you can't neglect surface tension, right? But you might have solved some problem earlier that the air pressure at the same level is same. I mean, pressure is the same, but in reality it does not happen, right? Internal pressure is higher than external pressure. Done? Okay. Right. Below this, write down considering equilibrium of a hemispherical part of a liquid drop a liquid drop in air, comma, considering equilibrium of a hemispherical part of a liquid drop in air, comma, right? So this is really important. Do you remember we take like a string loop and we needed to find the tension built inside the string loop, right? So what did we do? We took only half of the string loop, right? We didn't consider the whole loop, because if we consider the already the all the forces are balanced, we won't be able to figure out some internal things, right? So here as well, I'm not going to take the whole bubble. I'm only taking half of that, so we can think about the internal stuff there, right? So I'm taking half of that. So this is half of the bubble, right? So this is half of the bubble. So what do we have? We know that internal pressure, it is P1, external pressure P2. Okay. So how does the pressure forces are acting on, right? We know that pressure forces are perpendicular to the surface, right? So if you think about internal pressure forces, they are acting perpendicular. This is a 3D image, okay? It is acting on the hemisphere perpendicular to the surface. And external pressure also is perpendicular from the other side. From the other side. Okay. Then we know that P1 force, P1 is higher, P2 is less. So it is not balanced, right? So this can be pushed to this side. But it is balanced by the other half of the sphere. Other half means by the surface tension forces that are caused by the other half, like this. If you don't understand, let me know, right? So these are surface tension forces. So this pressure difference is balanced by surface tension forces caused by the other half. Do you understand that? Right? So how do we write this? If we think about internal pressure, right? Let's apply a force balance here. So you know that this pressure force, you can separate or resolve into two components. There are horizontal components and vertical components. There's a similar force at the top as well. So that this vertical component and this vertical component cancels off. So only remaining forces will be horizontal forces, right? Then all those forces around the hemisphere, those are pressure forces, you need to project to this side. I'll draw a separate image. If you project them, so what's the area that it applies? You need to consider this area. Understood? This area. Because you are only considering these components, right? So it is true for pressure forces here and pressure forces here. Internal pressure forces and external pressure forces. Okay, first I'll consider this P1. So P1, so we know that force is equal to pressure times area, right? So P1 is the pressure. What do we use the area? Area is this area, right? This area. So that is pi r squared. So this is the total force caused by this P1 pressure. Then if you think about P2, same case, but it is to the opposite side, right? So forces to this side equals forces to this side. This side means P2 pi r squared. P2 pi r squared to the opposite side. And surface tension forces also to the same side. So what is that? T times length. What is the length? Length of this circle. There's a circle. That is 2 pi r. Got it? Then you can get rid of this pi. Then when you simplify this, you get P1 minus P2. You can take this term here, P2 equals 2T divided by R. You need to remember this equation. So this is the pressure difference. Pressure difference, that is 2T divided by R. Take it down. If you have a problem, let me know. Okay. Below this, write down when R is less, delta P means P1 minus P2, delta P is higher. Take it down. So you can see, right, it is inversely proportional. Pressure difference is inversely proportional to the radius of the bubble. So smaller the bubble, higher the pressure difference. Do you understand that? Smaller the bubble, higher the pressure difference. Okay, write it down. Okay, we'll try a question. Write down Q. Write down, find the excess pressure. Find the excess pressure in a water drop. Excess pressure in a water drop with radius 3.6 millimeters. With radius 3.6 millimeters. Okay, quickly find that. So what's the equation? Delta P equals 2T divided by R. Find the excess pressure. Find the excess pressure in a water drop. Find the excess pressure in a water drop with radius 3.6 millimeters. 3.6 millimeters. Okay. You can use this equation, right? 2T over R. And tell me the answer. Okay. Yeah, 40 Pascal, right? 2 times 7.2 minus 2 divided by 3.6 millimeters. So 40 minus 1, yeah, 40 Pascal. Understood? So there's a 40 Pascal pressure. There's a pressure difference. Excess pressure inside it should be, outside pressure plus 40. The pressure inside is more than 40 Pascal, right? If you consider a water drop with the radius 3.6 millimeters. So it's a small water drop, right? So that's a large pressure difference actually. Is smaller the drop or the bubble, higher the pressure difference, higher the excess pressure. Okay, we'll try another question. Another question, write down. Find the internal pressure. Find the internal pressure of an air bubble. Find the internal pressure of an air bubble with radius 2 millimeters. 2 millimeters at a depth, at a depth 3 meters. So there's an air bubble here. It is at a depth 3 meters, right? So what they ask is internal pressure. Okay. Radius of it is 2 millimeters. Okay, try that. So let's say internal pressure is P or something. Okay. There's atmosphere above it. So this is like water. There's atmospheric pressure here. You can use 10 to the power 5. Just try that, I'll explain then. Okay. Okay, now listen. So this is atmosphere. It has PATM, right? 10 to the power 5. And at a 3 meter depth, it causes a pressure difference. That is hydrostatic pressure. Hydrostatic pressure. We can find that using H rho G, right? So if you think about pressure here, external pressure, it should be PATM plus H rho G. PATM plus H rho G. You know that from hydrostatics, right? So that's the pressure at this level. Then what should be the internal pressure? We know inside the bubble, inside the bubble, pressure is higher. By how much? Inside the bubble is pressure is higher. You need to understand whether it is higher or lower. We know that inside the bubble pressure is higher. By how much? It is higher by 2T divided by R. So what should be the pressure inside it? External pressure is this much, PATM plus H rho G. Then we need to go inside. So external pressure is PATM plus H rho G. When you go inside, it is higher 2T divided by R amount than this pressure. Okay, then you just have to simplify this and find the answer. If you have a problem, ask me. So atmospheric pressure 10 to the power 5, height is 3, water 10 plus 2 times 7.2 minus 2, radius 2 millimeters minus 3. So when you simplify this, 130,000 plus 72, 130,000, 72 pascals. If you didn't understand, tell me, right? This is the internal pressure of the air bubble, not external pressure. External pressure of the air bubble is PATM plus H rho G. That is found using hydrostatics, right? Using for hydrostatic, you can find the external pressure. To go inside the bubble pressure is, we know that it is higher by 2T over R. So you just have to add that, right? If it is higher, you just have to add that amount. So if they're given internal pressure and you need to go outside, you need to subtract this much, because this is the pressure difference, 2T over R. If you're done, thumbs up. Okay. Then write down a point. A soap bubble has has two free surfaces. A soap bubble has free two surfaces in contact with air. A soap bubble has two free surfaces in contact with air. We learned that earlier, right? So here you have the soap liquid layer. Here air, liquid, and again air. So what do we have to do? At the earlier cases, we just multiplied by 2, right? So let's see what happens here. So we need to make, let's say the radius is simple r, internal pressure P1, now external pressure P2. So this is in air, right? So bubble is in air. This is external pressure, this is internal pressure. Here as well, internal pressure is higher due to surface tension. But we don't know how much, right? Because this has two free surfaces. So for that as well, we can derive an expression or an equation. So for that, we take half of this bubble, right? When you take the half, it's like this. Right? And actually this has a soap liquid layer here. Similar to the previous case, internal pressure is P1, external pressure is P2. So we know as before, P1 is acted perpendicular to the internal surface of the hemisphere. But when you take the components, that adds up to this area. I explained it at the previous case as well. So these are the pressure forces, right? These are pressure forces, internal pressure forces and external pressure forces. Since P1 is higher, P2 is lower, there's an unbalanced force to this side. But that unbalanced force is balanced by what? Surface tension. But there are two free surfaces, right? Like these are the forces by one surface. Then there's another surface, internal surface. There's an internal surface as well. Got it? Okay, now let's balance this out. So what is the forces to this side? P1 multiplied by area. Force is pressure times area, right? So the area you take not the area of the hemisphere, but the area of this circle, right? So it is pi r squared. So that is the force to that side, equal to forces to this side. So the pressure forces P2 phi r squared. Then surface tension forces. How do we find the surface tension? T times length, right? Surface tension times length. So what is the length? Circumference of this circle. That is 2 pi r. We need to double this force. Why? We need to double this force. Why? There are two free surfaces. So you multiply this by 2. Can you see that? Two pi r multiplied by 2 as well, right? This is times 2, right? Right. Then when you simplify this is what you would get. P1 minus P2 equals 2 times 2, that becomes 4 actually. 4t divided by simple r. So when you have a one free surface, it is 2t divided by r. But when you have two free surfaces, it is 4t divided by r. So remember those equations. Take it down. So you should be able to derive these as well, right? So you have to clearly understand. So if you're done, thumbs up. Thumbs up if you're done, right? Tishida, are you done? right? Uh, so just remember that, right? At least you need to remember the equation, but derivation also is essential, right? Okay, write down a question Q. Write down. Find the excess pressure. Find the excess pressure in a soap bubble. Excess pressure in a soap bubble with radius 2 millimeters, with radius 2 millimeters, within brackets surface tension given for soap, that is 2.5 10 to the minus 2 newtons per meter. Okay, find it quickly and send me the answer. Yeah, 40. Okay, so delta P equals 40 over R. 4 times tension 2.5 minus 2. Radius is how much? 2 millimeters. Two millimeters, right? Did you get a 50? Yeah, 50. Yeah, it is 50 pascals, right? Right. So whenever you have like a soap bubble, or it could be a meniscus. Remember those liquid meniscuses? You can use this equation, right? You can use this equation. Write down point. There is a pressure difference. There is a pressure difference. There is a pressure difference between two sides of a liquid meniscus. Two sides of a liquid meniscus. There is a pressure difference between two sides of a liquid meniscus. So for acute angle, I'll explain that for acute angle, when the contact angle is acute and when the contact angle is obtuse. So what's the shape? When it is acute, shape is like this, right? When it is acute. Actually, you can extend this meniscus. You can extend this meniscus and it will be you can draw a sphere like this. Let's say for this one, meniscus is like this. Also, again, you can extend the meniscus. So this we call a concave. This is a concave shape. This is a convex shape, right? And you can apply the same equation for both. Pressure difference P1 minus P2, it is equal to 2T divided by capital R. The only difference is here we are applying capital R. What is the capital R? So for the previous case, for the soap bubbles, for the liquid drops, you just use the radius of that. It's fine, right? But here capital R is always should be not the radius of the tube, right? It should be radius of the meniscus. So the radius of meniscus, how do you find that? You extend and draw a sphere and you get the radius of that. So you always substitute that here. So capital R is what? Radius of meniscus. Radius of meniscus, not the tube, right? Radius of meniscus, capital R. That's all you have to do to find the pressure difference across a meniscus. Take it down. Take the whole thing. So you have to remember this stuff according to the pattern, right? Otherwise you will forget this. So you need to understand the radius of the internal radius of the tube and the radius of the meniscus, right? If you're done, thumbs up. Right. Below this, write down. Below this, write down. When phi equals 0, when phi equals 0, within brackets hemispherical, within brackets hemispherical, comma, radius of curvature of meniscus, radius of curvature of meniscus, within brackets capital R, within brackets capital R, is equal to radius of the tube, within brackets simple r. Okay. So what happens when this is 0? Contact angle is 0. What's the shape of the meniscus? You know it takes a hemispherical shape, right? Hemispherical shape. When the contact angle is 0, right? Here the contact angle is 0. So if you extend this, it becomes like this, right? Completely inside the tube. And if we consider the radius of the meniscus, you can see the capital R and simple R is equal. Understood? You can see that, right? Simple R and capital R equal. Write it down. Draw it and write capital R equals simple R. Okay. So you have to think about reasons for this, right? Reasons for this as well. And if you don't understand, ask me. Right. So earlier we derive an expression for capillary rise using pressure balance. Sorry, force balance, right? Here I'm going to get an expression for pressure using pressure difference, right? Write down subtopic. Expression for capillary rise. expression for capillary rise using pressure difference. Expression for capillary rise using pressure difference. Right. So it is a capillary rise. We know contact angle is acute angle. Then let's say you have a meniscus in this shape, like this. Okay. Then you can extend this into a sphere. Okay. Then if you draw the tangent, here you have the contact angle. Then I can draw this triangle. So half of that triangle, half of this length is simple r, that is the internal radius, right? So let's say center of the circle is here. Then you can draw these lines. Then you can have this triangle. So this is 90 degrees, 90 minus 5. Here then it becomes contact angle. First draw that one. Here you have the radius of meniscus. Here you have internal radius of the tube. Actually you can draw that triangle separately. This is capital R and this is simple r. Draw it carefully, draw it. You have to understand that, right? As you are drawing, you need to understand what you are drawing. If you are done, thumbs up. Right. So you have this small triangle, right? This triangle. So using that triangle, you can write cos contact angle equals adjacent side is simple r, hypotenuse capital R. You can have that, right? Let's say, so you can see capillary rise is measured from here to the bottom of the meniscus, right? Bottom of the meniscus. You need to pay attention to that, right? Not the top of the meniscus, bottom of the meniscus. Let's say slightly above the meniscus, let's consider point A. Slightly below the meniscus, I'll consider point B. Okay. So what's the pressure slightly above the meniscus? It is open to the atmosphere, right? So I can say PA equal to what? Atmospheric pressure. It is open to the atmosphere, right? PA is equal to atmospheric pressure. Then how do we write PB? PB you can write like this. PA minus 2T capital R. How did I write it? Do you remember always at this side pressure is higher, at here pressure is lower. So whenever you take a meniscus or something like this, here pressure is less, here pressure is higher. Remember the water drop or the soap bubble? Always to the curved side, inside the curved side, pressure is higher. At the other side, pressure is lower. By how much? 2T divided by capital R. So we know the pressure here is PA, slightly below that meniscus. Pressure should it be higher or lower? Slightly below. It is curved like this, right? So the pressure should be less, slightly below that. So it is less 2T divided by R amount. So PB pressure, you can write it as PA minus 2T over R. Do you understand that? So you should be able to write these pressures, right? Otherwise, it is not possible to do the questions. Okay. So from this, you can say PB equals PA is PATM. So PATM minus 2T divided by capital R. Okay. So we have a pressure for PA and pressure for PB. Then let's consider this level, C and D. Let's say this is C and this is D. So this is at the same level, right? There are no meniscus here. So pressure at here and pressure at here same. It is only hydrostatic pressure. PC equals PD. We can write PC equals PD. Because same level, right? There's no surface tension acting to these two. So at the same level, pressure also is equal. PC equals PD. So how do we write PC? You can write PC. You already have an expression for PB. PB plus H rho G. As it goes down, pressure increases, right? So the hydrostatic pressure should be added by H rho G. So PB is PATM minus 2T divided by R. PATM minus 2T divided by R plus H rho G. So that is PC. Then what is PD? PD is PATM. It is open to air, right? PD. So it should be just PATM. Okay. Then PATM cancels off. Keep H rho G here. And take this term to the other side. 2T over R. We are getting the same equation, right? Again and again. H rho G equals 2T divided by R. Understood? So from this, you can find capillary rise. Earlier as well, we got the same thing, right? The only difference is here it is capital R, right? Capital R. That's the radius of the meniscus. Okay, take it down. If you don't understand something, let me know. These pressure balances you should be able to do, right? So we end up with the same equation there. 2T divided by capital R. If you're done, thumbs up. Right. Below that, right? Below that, right? Below this one, right? Since we know that cos pi is equal to what? Internal radius divided by capital R, right? So instead of this is 1 over R, instead of 1 over R, what can you write? So 1 over R is equal to cos pi divided by simple R. So when you substitute it here, instead of 1 over R, you can put cos pi divided by simple R. What do you get? 2t divided by simple R, cos pi comes here. So this is the another equation, right? Same equation. Here it is the meniscus, radius of the meniscus. If you need to use the internal radius, there's going to be cos pi there, right? Take it down. So all these equation we derived earlier, right? Using force equilibrium. This is pressure balance. Both ways you have to master, right? Thumbs up, okay. Right. So we discussed about capillary rise, right? So we derived an expression for capillary rise. Similarly, we can derive an expression for capillary fall. Write down. Deriving an expression for capillary fall. Deriving an expression for capillary fall. So for capillary fall, it is like this. So for a fall, it is a meniscus like this, and the liquid level here. So slightly above the meniscus, we have point A. Below the meniscus, we have point B. And then we can extend this sphere like this. And again, we can draw that triangle, right? So when you draw that triangle, we know that this alpha and this alpha is equal, right? This is not contact angle, okay? Contact angle is actually obtuse here. This is the liquid. This is like mercury, right? Air, these are air, right? This is air. In this space, it is air. Around it, it is mercury. Right? Then let's consider a point here C and a point at the level B. Let's say it is D. Okay? So we are going to do a pressure balance now. So for this triangle as well, we can draw, I can enlarge this triangle and get alpha. Then this is going to be simple r. This is going to be radius of the curvature, meniscus, right? Then similarly, cos alpha is equal to simple r divided by capital R. This alpha is not contact angle, right? Contact angle is this much. It is an obtuse angle, but I'm not going to use the contact angle here. It will be confusing, right? So I'll just use this as a just an angle that. So this whole thing is the contact angle, right? Do you understand? This thing is the contact angle phi. So using that, you can see this total angle is 180. 180 minus alpha is the contact angle. It will also be useful. 180 minus alpha is the contact angle here. Okay. Press draw that and thumbs up if you have to understand the image first, right? Around it, it is the liquid. Here, that is air, atmosphere. Okay, take it down. If you're done, thumbs up. Tishilda, I done. Tishida, right? Tishida. Right. So now I'm going to do a pressure balance. And you need to derive the earlier equation, right? Okay. So what's the pressure here? This is open to the atmosphere. So we can say PA is equal PATM. Open to the atmosphere, point A. Then point B. So what is the pressure at point B? It is slightly below the meniscus. So it is curved to this side. So the pressure at B should be higher than A. By how much? 2T divided by capital R. So here pressure is PATM plus 2T divided by capital R. That's the pressure at B. Right? Then we can write PC equals, that is open to atmosphere, PATM. PC equals PATM. Then PD, just using hydrostatic, right? PATM plus, this height is simple h. PATM plus h rho g. H rho g, right? Sorry, that is PD, right? PD. PD equals PATM plus h rho g. That is just hydrostatic. Then other thing, we know what? PD and PB should be equal because same level, right? This is the same liquid. So at the same level, pressure should be equal. What is that? PD equals PB. Same level. So what is PD? PATM plus H rho G equals PB is PATM plus 2T divided by capital R. PATM cancels off. Again, what do you get? H rho G equals 2T divided by capital R. Okay? 2T divided by capital R. right? Then you can write another equation. Since cos pi equals simple r divided by capital R, you can substitute it here. Then what happens? H rho g equals 2t divided by simple r. Here you get cos phi. This is internal radius. So this is radius of the meniscus. This is internal radius. If you need to write the equation in internal radius, you need to have cos pi here. Okay, take it down. Sorry, cos alpha, right? I use cos alpha. Cos alpha, right? Here. Thumbs up if you're done. Okay, so we derived actually the same equation, H rho g equals T2 divided by capital R or 2T cos pi divided by simple R if it is internal radius. That is for the capillary rise, right? So you know that when you have a certain tube and a certain liquid, there must be a certain amount of a capillary rise, right? There must be a certain amount of a capillary rise. In the next part, we are going to discuss what if the length of the capillary tube is not sufficient to contain the capillary rise. Do you understand that? What happens if the length of the capillary tube is not enough to contain the capillary rise, right? So that is what we are going to discuss. Meaning of that, let's say, for an example, right? Let's say when you immerse this tube, there's going to be like a 50 millimeter capillary rise according to the equations. But this height is 25 millimeters. So what could happen? Liquid goes up. It doesn't flows out like this, right? What happens is it changes the shape of the meniscus. So there more liquid can go through this capillary tube upwards, right? But the length of the tube is not enough, right? So in that case, usually the liquid does not flow out like this. What happens is there has to be a certain shape of the meniscus. What happens here is it changes the shape of the meniscus because there's pressure here, more pressure, and it pushes the meniscus upwards. That is something, that is what happens there, right? Okay, so we'll discuss that in detail. First write down, put asterisk mark, write down. For a capillary rise, comma, for a capillary rise, comma, if the length of the pipe above the liquid level is less than capillary rise is less than capillary rise, simple H, capillary rise, simple H, comma, liquid rises to the maximum length, and changes capital R and phi, that's the contact angle, right? Capillary capital R and phi of the meniscus, capital R and phi of the meniscus. Done. So usually that does not happen, right? Meniscus remains the same regardless of the rise. But if the length is not sufficient, then the shape of the meniscus is going to change, because there's a pressure here, external pressure, excess pressure, right? It pushes the meniscus upwards, changing the shape of the meniscus like this, right? Liquid is pushing from through the pipe, changing the shape of the meniscus. Okay, right. So let's write the equation. H rho g equals 2t divided by r. 2t divided by r, right? So according to this equation, so by force, this H and R has the inverse proportionality, right? H and R. Here what happens? There's a certain amount of a capillary rise, but since the length is not sufficient, by force, H is reduced. Capillary rise is reduced. Understand? Capillary rise is reduced. Okay? Then what should happen? Capital R, that is the radius of the meniscus, has to increase. Okay? So this is a one way to explain that. Meniscus decreasing means what? I mean, radius of the meniscus decreases. Let's say shape it like this. Sorry, it increases, right? And a small circle. When the meniscus becomes like this, is a large circle. So the radius increases. And with time, what happens? Meniscus gets this shape, right? So the radius keeps increasing. Do you understand that? This H is decreased by force. By force means you are not allowing H to increase to that the certain level, right? You are not having the total length of the capillary tube, right? So H is decreased. So there's no option now. So capital R increases, right? Right. Below write down, since, write down, don't write these, right? Since H proportional to 1 over R, since H proportional to 1 over R, when H decreases, R increases. Meaning shape becomes like this, right? When H decreases, R increases. Then according to the another equation, here you have simple R and here you have cos phi. According to this one, these are constants, right? then h is proportional to cos phi. Then below that, right, since h is proportional to cos phi, when h decreases, what happens? Cos pi decreases. But when cos pi decreases, what happens to the angle? Angle increases. Remember trigonometric ratios? When cos value decreases, angle increases. Contact angle increases. Take it down. Angle increasing means the same thing, right? Meniscus, spherical shape gets larger. Right? So with time, contact angle is increasing, right? Or capital R is increasing. So we'll see what happens there by an image. Let's say here, right? Let's start from a hemisphere. Let's say contact angle is 0 degrees here. 0 degrees. So you have a hemispherical shape. What you do is you immerse this tube further a little bit, right? Like somewhat here. So what's the required capillary rise? It's this much, right? Required capillary rise is this much. That capillary rise must maintain inside the tube. So here also it should be the same capillary rise. When tube is lowered, still it can have the capillary rise. It can have the same capillary rise because the length is still enough for the tube. We are pushing down the same tube, right? Same tube. Then I will further, still a contact angle is 0. Then I will push it further downwards. Notice these lengths, right? I'm gradually immersing the tube. Now what has happened? Now it is not enough. Now it starts to change the contact angle. Right? Starts to change the contact angle. And further you immerse, contact angle further changes. Right? Then when you get the tube to this level, actually what level becomes like this. So you have gradually immersing, you've been gradually immersing the tube, right? So here and here, same contact angle because length is sufficient. Once it passes this level, then the contact angle starts to increase. Notice, it starts to increase. Okay, take this down and thumbs up once you draw that. This is only valid once the length of the pipe is not sufficient, right? Before that, you can't use this. If the length is not sufficient, then only contact angle starts to change. Draw it and thumbs up once you're done. You have to correctly show this that it is immersing, right? Thumbs up if you're done, right? Right, so regarding this, we'll do a question. Write down Q. Write down a liquid with phi equals 0. Phi means contact angle, right? A liquid with phi equals 0 is inside the capillary tube and its capillary rise is 10 centimeters. Capillary rise is 10 centimeters. Full stop. But the length of the tube above the liquid surface is 5 centimeters. Above the liquid surface is 5 centimeters. In this case, find the contact angle. Okay, try that. You can use this, right? H is proportional to cos alpha. Sorry, cos phi. Right? Apply that and find the new contact angle. So you have two cases. Apply the proportionality to the two cases and find it. Send me the answer once you find that. So what they ask is new contact angle, right? Just apply this proportional to two cases. Two cases. So the first case, what is that? Capillary rise 10 centimeters, right? What's the contact angle? Cos 0. Second case, capillary rise is limited to 5 centimeters. Then what they ask is the new contact angle, let's say cos pi. First, second, divide 2 by 1. What do you get? 5 over 10 equals cos pi divided by cos 0. What's the value of cos 0? Cos 0 is 1, right? So 1 over 2 equals cos pi. So what should be the new contact angle? It should be 60 degrees, right? Did you understand that? Thumbs up. Get it? So this contact angle changes only in this case, right? If the pipe is not sufficient. Otherwise, contact angle is a constant for a given pipe and a liquid, right? It changes if the length of the pipe is not sufficient. There's no any other option, right? That's why it changed. So it is a one that scenario you have to clearly understand what if the pipe is not length is not enough to contain the capillary rise, right? Then we'll move on to the next scenario, right? These are important. They ask questions from this right? Write down the topic. Inflating a liquid bubble, inflating a liquid bubble at the end of a tube, at the end of a tube, by slowly blowing air, by slowly blowing air. Okay. Right. So vertical tube, right? This could be a soap layer, or it could be there could be water inside it, a liquid inside it, right? Let's say you have a soap layer here. It does not matter, right? So initially, what do you see? Let's say you slightly blow air. What happens to the meniscus? It could be like this, right? As a slightly curved downwards. Then I can complete the meniscus, this meniscus like this. Let's say that is simple A. Then I further blow air. Then the meniscus could be like this. right? Then again I can complete the sphere regarding the meniscus. So you can see radius is getting smaller, right? Then I further inflate this. Meniscus become completely hemispherical. Completely hemispherical. And if you extend the meniscus, it is a complete sphere inside. Now the radius is equal to the internal radius of the pipe. So let's say that is simple C. Okay, that is simple C. Usually, when it comes to simple C, this breaks down, right? This liquid layer breaks down usually. But you might have seen in some cases that soap bubbles remains at the end. It further inflates. Let's say inflated like something like this. You first take this down and first draw these three till you get a hemispherical shape, right? First draw that, otherwise it will be confusing. First draw these three. I think you can see that, right? Yeah. There's A, B, and C meniscus, right? Till you get a hemispherical shape. Thumbs up once you're done. Thumbs up if you're done, right? Right. Now I'll use a different color. After hemispherical shape, in most of the time this will break down here, right? I mean, this layer will break at the hemispherical shape. But in some cases, it inflates further. Let's say it inflated something like this. This is a different color, right? This is the meniscus. This is the extension. And let's say again it inflates further. These could be D and E. Then you can extend the sphere, complete the sphere. Understood? Okay? Okay, take this down. Take this down. You are done, right? Write down. With time, comma, radius of curvature, capital R, decreases. Then below that, right, at C means hemispherical, right? At C, capital R is minimum. At C, capital R is minimum. To the same line, right? R equals simple R. At this case, R equals simple R. Hemispherical. Hemispherical. To the same line, right? Pressure is maximum. Pressure is maximum since pressure is maximum since capital R is minimum. Pressure is maximum at since capital R is minimum. Remember this, delta P equals 2T over R, right? So R is minimum, pressure difference is highest. So everything when it is C, when it is hemispherical. Then below that, right? after C, comma, bubble can break, at any moment. Bubble can break at any moment. Therefore, final instance of stability is at C. Okay, is at C. Then, so we know this equation, right? 2T over R or 4T over R, it doesn't matter. Okay. So according to this, if R decreases, delta P increases. If it increases, delta P decreases, right? So according to that, as the bubble inflates, what happened to the radius? Remember, with time, initially it had a higher value, right? Then it comes to the lowest. That is the internal radius, simple R. After that, what happened to the radius? It increased. Remember that? It started from a large sphere, right? Higher radius. Then gradually it decreased to the hemisphere. Then comes to simple R. Then after achieving the hemispherical shape, if you further inflate that, again it starts to, that sphere starts to enlarge, right? Further it increases its radius. So this is how the radius changed with time as you inflate it. So what should happen to the pressure, internal pressure? We know that when radius decreases, pressure increases, right? Pressure increases. Then radius increases, pressure decreases. Internal pressure decreases. Draw these two graphs. This is internal pressure. So P max is achieved at hemispherical shape, right? Pressure is maximum. That's why it could break at that point. Take it down. Thumbs up if you're done. Done? These are really important, right? Again, at home, you can study these and try to understand these, right? These are like really important. Usually, these is stuff always students neglect, right? But if you learn this, actually, these are the stuff they ask questions from, right? As you study the note, it will be more clearer. It will be clearer as you're learning this, right? Okay. So using this one, we'll just do a question. Write down Q. Find the maximum height. Find the maximum height water can be filled. That water can be filled into a container. Into a container. Into a container with a small punch. With a small punch at the bottom of 0.5 0.4 millimeters. 0.4 millimeter radius. 0.4 millimeter radius. Okay, read the question and try to do that. It's water, so you can use 7.2, right? 10 to the power minus 2. So there's a container like this, right? Then there's a punch. Just because there is a small punch or a hole, it does not mean water leaks out of this. Why is that? Because surface tension, right? Let's say you fill this up to here. Surface tension forces can hold this liquid. This pressure difference, it can hold. The surface tension forces can hold up till this gets hemispherical shape, right? So at the hemispherical shape, it has the maximum pressure difference, right? So that way you can find the maximum height that you can fill the liquid. You just have to do a pressure balance here, right? Okay, try that. You have to find H max. Outside it is atmospheric pressure outside. Let's say this point just above the meniscus A, below B. So we know that PA minus PB is equal to 2T divided by simple r. We don't need cos pi because this is a hemispherical shape, right? So it is just 2T divided by simple r. Phi is 0 there because hemispherical, right? So what is the way to write PA? Go through the liquid. So that is P atmosphere plus H max rho g. That is PA. Minus PB. It is just air, right? Here. So it is PATM equals 2T divided by R. PATM cancels off. H max rho g equals 2T divided by simple r. Then you have to find H max. Okay, find that. If something is not clear, let me know. Tell me the answer. Is it centimeters or meters? Let's see. Two times 7.2 minus 2 divided by 10 to the power 3 2 divided by r rho g, right? Rho 10 r is what? 0.4. Yeah, centimeters, correct. So it is 3.6 centimeters, right? Yeah, it is correct. Okay. So there's a one more phenomena that we have to discuss, right? Right. Write down the topic. Write down the topic. Height of a liquid column. This also is extremely important, right? Write down. Height of a liquid column. Height of a liquid column in an open capillary tube. Height of a liquid column in an open capillary tube. First, write down this paragraph. Write down. Let's say a liquid with phi equals 0, contact angle 0, right? Let's say a liquid with phi equals 0 is put into a capillary tube. is put into a capillary tube. Full stop. Meniscus at the top is hemispherical. Meniscus at the top is hemispherical. Since phi equals 0, right? Since phi equals 0. Full stop. Depending on, to the same line, depending on the liquid column height, depending on height of the liquid column, depending on the height of the liquid column, comma, shape of the meniscus, shape of the meniscus at the bottom, shape of the meniscus at the bottom changes. Shape of the meniscus at the bottom changes. Right? Done, right? Okay. So this is what we are going to do, right? You just take an open tube. Both ends are open, right? Like both ends are open tube. Then you enter some insert some liquid into it. Let's say water. So what happens is, so there's a water column here, right? It doesn't just drop. Okay, it doesn't just drop because of surface tension forces. There's a meniscus. When you have a liquid column, you can see you're keeping it vertical. Top meniscus. Then there's a bottom meniscus. Right? Top meniscus is under zero weight, right? Above that meniscus, there is no weight. So this top meniscus will always have a hemispherical shape. It will always have the same shape, hemispherical, because contact angle is 0 there, right? It will have a hemispherical shape. This bottom meniscus, what happens to the bottom meniscus? There's a water column above it, right? So the shape of the meniscus changes depending on the height of the water column above the bottom, right? So the bottom meniscus changes shape, top meniscus does not change, right? So here I'll discuss that under three circumstances, with the behavior of the bottom meniscus. We don't have to consider the top meniscus, right? It is a constant shape. Under changes of the bottom meniscus, we'll discuss this. Okay. So first let's write simple A. Simple A, this is the first case, right? Simple A, write down. When bottom meniscus, let's say bottom meniscus, right? When bottom meniscus is flat, when bottom meniscus is flat, right? Okay. So you have the tube, both ends open. Top meniscus, it is spherical because contact angle 0, right? But due to the weight of this liquid column, what happens to the bottom meniscus? Let's assume it becomes flat, right? Actually, its contact angle becomes 90 degrees because of the weight of this liquid column, right? Understood? Then Let's consider this point A, slightly below it is B. Then let's say this height is simple h. We measure this height always through the liquid, right? Not this h is not up to A, it is up to B, right? From this, it is the height of the liquid column. Okay, only through liquid we put this h, not up to B. Sorry, not up to A, it is up to B always. This h, right? Then slightly above this, let's mark a point C and another point D, slightly below this point. And I'm going to measure the pressure along this line, let's say from X to Y. So that is what I'm going to do. First draw this. I'll explain it, leave space here, right? I'm going to explain it here. First draw this. Radius is simple R, internal radius. So as you're drawing, you have to understand what this explains, okay? Thumbs up, right, if you're done. This is the last theory part here, right? Thumbs up if you're done. Right. So I'm going to analyze pressure along this line, right? And I'm going to derive an expression for simple h. It's going to be the same as before, but let's derive that. So what is PA? Open to atmosphere. So it should be PATM, right? Then what should be PB? So you should be able to write pressure at any point, right? You need to practice that actually. So PB is equal to, here the pressure is PA. So once you jump the meniscus, pressure is decreased because curvature is inside, right? Outside pressure is less. By how much? 2T over R. So you can say pressure at B is equal to PA minus, not plus, right? Minus 2T over R. We don't need cos pi. Why? Because it is hemispherical, right? Yes, you can write 2T over simple R. Then we know PA is equal to PATM minus 2T over R. So that is pressure for PB. Pressure at A, pressure at point B. Then let's try the pressure at C. How do we write that? So if we know the pressure at B From here to here, what happens? It is hydrostatic pressure, right? It is just the liquid column. So that pressure you can find using H rho g. So PB plus H rho g should be equal to PC. Got it? Then I'll write pressure for D. It is open to the atmosphere, PD. It is PATM. Okay, PATM. What about this meniscus? Bottom meniscus is flat. So why does this meniscus curve? If it curved to this side, pressure here is higher than pressure here. That's why it curve like this, right? If it doesn't curve, what does it matter? What? Uh, why is that? If it doesn't curve, pressure here should be equal to pressure here, right? Understand? If pressure is higher here, it curves upwards like this. If it doesn't curve, it means pressures are equal at PC and PD. Got it? So what is PC? Actually, I can write for PB from here. PB is PATM minus 2T over R PB plus H rho g. So instead of PC, I can write this. PATM minus 2T over R plus H rho g. Then for PD, it is PATM. PATM cancels off. What do you get? H rho g equals 2T over R. Same equation, right? Same as before. You get H as 2T divided by R rho g. You don't need to remember this, right? You just have to know if the bottom is flat. Given that the bottom is flat, the maximum, not the maximum, the water column that you can hold is equal to capillary rise. Same equation we got, right? So H is this much. Okay, take it down. Thumbs up if you're done. Okay. Below this, right? This is equal to the capillary rise when the tube is immersed vertically in a liquid. Okay. Right. Then I am going to draw the pressure variation from X to Y, right? This is pressure. Here X, here Y, right? From X to Y, right? From X to here, wait, right? Okay. From X to point A, what's the pressure? Atmospheric pressure. It's a constant, right? It's a constant. So this point is A. This point is A. So once you go to B, what happens? Suddenly, right? Without, it is just the thickness of the meniscus. Suddenly, pressure drops. This is atmospheric pressure. Suddenly, pressure drops. By how much? By 2T over R. This much. Now the pressure is PATM minus 2T over R. This point is point B. That's the pressure at point B. Then we further go down. As you go down in a liquid, hydrostatic pressure gradually increases with the height, right? It increases like this. Then this is C. We know that at C and D, pressures are pressure equal, right? And what's this pressure? ATM, right? PATM. And pressure here also should be ATM. Then after that, pressure is atmospheric pressure. Same level. Understood? Take it down. This is both C and D points. Here the hydrostatic pressure, right? That's why pressure increases, then constant. Take it down, the graph. Okay, so that's all about when the bottom meniscus is flat. You drew the graph, right? Thumbs up. Okay, so simple A case, that is when the bottom is flat, right? Then there's another case, simple B, when, let's say now the liquid column is H dash. For the previous case, liquid column was H, right? Now we fill the tube with a less height, less than simple H, right? If previously it was 12 centimeters for the previous case, now it is like 7 centimeters, right? So what could happen? Top meniscus does not change. It is hemispherical. It is not under any influence, right? So it remains same hemispherical shape. Initially it was flat, right? Now this has a less height, meaning less pressure. So this can bend like this. So the surface tension forces are powerful here, more than hydrostatic pressure forces, right? So the meniscus gets this shape, right? The hydrostatic pressure is less now, right? So it cannot push the meniscus downwards like this. So the surface tension forces are somewhat powerful here. So it bends inwards and keep the contact angle to an acute angle at the bottom as well. it is not hemispherical, right? Both sides cannot be hemispherical. Here the contact angle is 0, here the contact angle is more than 0, right? Due to this, there's a hydrostatic pressure here. Now this height is h dash. Then I'll complete this meniscus. Let's say now the radius is r dash for the meniscus. I'll mark these points along xy. I need to analyze the pressure from x to y. This point D, this point A, just below B. This h dash is between B and C, right? Up to B and C. H dash is measured only through the liquid, okay? B and C. Right, take it down and thumbs up once you get it. Thumbs up if you draw that. You have to understand, right, what you are drawing, okay? Don't keep it for like to refer later. Just try to understand the maximum amount at the class. Right. Now I'm going to do a pressure balance, okay? I'm going to come from here to here, A to D. So we can write PA, it is atmospheric pressure, is equal to PD, right? PD. It also is atmospheric pressure. No, I'll just start from here. So what's the pressure here? PATM, right? PATM. Slightly below. It is less 2T over simple r, internal radius. Slightly below, right? Then hydrostatic pressure. It increases by how much? H dash rho g as it comes to C. Then after C, pressure at this side is higher, right? So you have to add 2T divided by meniscus. Now it is meniscus. This is not hemispherical, right? So you can't use internal radius. You need to get the radius of the meniscus. So it is plus 2T over R dash. Why plus? Because pressure at here is higher, right, than here. So it is equal to PD. PD means PATM. I actually came from here to the outside, right? So I wrote the pressure coming from here like this. Then you can write the pressure at D coming from like this as well, right? So from outside it is just PATM. Then you can cancel PATM, but we cannot have a special equation from that, right? So I'll just leave it there. So if they ask a question, you just have to do it, right? Then we'll think about pressure variation from X to Y. X to Y. Right. From here to here, it is atmospheric pressure. Let's say this is point A. Right? Point A. Then pressure drops suddenly. By how much? 2T over simple r. So the pressure here is P ATM minus 2T over simple R. Then from here to here, pressure increases by this much, let's say. Up here B, then here it is C. It doesn't increase at C, it doesn't increase up to the atmospheric pressure. You can see outside it is atmospheric pressure. Pressure at C is less than atmospheric pressure, right? So for the hydrostatic pressure, it only increases up to C. It doesn't go to this level. Okay. Then it jumps to D. Then there's a sudden pressure increase because the shape is like this, right? Pressure increase. It is at the atmospheric pressure level. Do you understand the pressure variation? So you should be able to draw these graphs, right? P, C, D. Okay, take it down and thumbs up. Thumbs up if you're done. Right. Then another case, there are two more cases. C, write down C. That case is when now we fill the tube to H double dash level. This level is higher than simple H. You know, simple H is when it is flat at the bottom meniscus. So we discussed when this is equal to H, I mean less than H. Now we are considering when you put more liquid into it, right? More than the flat surface. What could happen now? What could happen? Top meniscus does not change, right? It is same as before. It is same as before, right? It is similarly hemispherical, it doesn't change. What happens to the bottom meniscus now? When H dash, it is flat now, right? If you have a liquid column more than H, hydrostatic pressures push this further and this bends downwards due to the weight of this. This is very heavier than that, right? This liquid column. So it bends like this. Then you can complete the sphere of the meniscus. Same as before, now let's analyze the pressure from X to Y. Okay. So now point A, point B, point C, point D. Okay. This height is h double dash. H double dash. Let's say the meniscus radius is r double dash. This is a different meniscus, r double dash. Okay, take it down. Thumbs up. You should be able to like analyze these pressure variations, right? On your own actually. Okay, if you're done, thumbs up. Thumbs up if you're done, right? Okay, let's analyze pressure. I'm not going to write the equations. I'll just show it in the graph, in a graph, from x to y, right? Okay, from x to A, atmospheric pressure. Then to the other side, sudden drop of pressure. Here PATM. Here sudden drop is what? Then the pressure becomes PATM. So this is A, this is B, right? PATM minus 2T over R. This drops by 2T over R amount. Okay. Then pressure gradually increases from B to C. B to C. Do you see that at C, pressure is higher than atmospheric pressure? Because it has bent like this, right? Pressure is higher than atmospheric pressure at C. So point C should be here somewhere. This is C. Okay. But the pressure difference is what? Then this is C. Sorry, C. Yeah. Then at D, what's the pressure? Drops to atmospheric pressure again at D. Then pressure is constant after D. Okay. You need to analyze these graphs at home again, right? At D. What's the pressure here? PATM plus 2T divided by R double dash, right? This pressure difference is R double dash. Okay, so that is how pressure varies along each point. So this graph gives you a full description of the pressure variation. Take it down. You have to draw these images, right? And analyze these again, right? Till you come 100% understand this. So thumbs up when you're done. Right. The final case, this is simple D. Simple D. So I'm going to put liquid into the tube further. I mean, I'm going to increase the height of the liquid further till the pipe can hold its maximum height of the liquid column. Write simple D when tube holds max liquid column. Write down. When tube holds maximum liquid column. Top meniscus, it is hemispherical, right? It's always hemispherical. Radius R. So I'm putting liquid as much as possible, right? So what's the maximum case? So initially this was like this, then became flat. Then finally the bottom meniscus became hemispherical, outward. What's the specialty when it becomes hemispherical? Now these two sides have the maximum pressure it can hold. If you put any more liquid, it will leak out of this tube. Okay. Right. Below this, write down when the bottom meniscus is hemispherical, when the bottom meniscus is hemispherical, comma, liquid column has the maximum height. Liquid column has the maximum height. Okay. Then I'll draw the pressure variation from X to Y. Now you know how to do this, right? X to Y. From X to A, B, C, D. From X to A, it is ATM, right? PATM. Then at B, sudden pressure drop. Now the pressure is PATM minus 2T over R. Then gradually increases. And you can see at C, pressure is higher, right? Which is curved to this side, pressure is higher than ATM. By how much? 2T over R. This is A, B, C. Actually, it is symmetrical here, like PATM plus 2T over simple R. Both are 2T over R, right? Because both meniscuses are same shape, 2T over R, 2T over R. Then at D, what happens? Drops to PATM. Then becomes constant. Right? So that's the variation. Okay, take this down and let me know. This is the H max, right? From B to C, from B to C it is H max. H max, right? From B to C it is the maximum height. Mention that as well. Thumbs up if you're done. Okay, let's do a pressure balance. There's a special point to this one. You have to learn that as well. I'll do a pressure balance, right? So I'm going to go from here to D, from point A to D, right? So what's the pressure at point A? Atmospheric pressure. Slightly below. At B, PATM minus 2T over R. Then from here to here, hydrostatic pressure. You need to add plus H max rho G. So that's the pressure at C. This is the pressure at C. Then go to D. To D, you need to subtract 2T over R. Okay. So now I am at D, right? So I just wrote pressure from A to B to C to D. This is the pressure at D. Pressure at D also is equal to PATM. Okay. PATM cancels off. What do you have here? Minus 40 over R. Sorry, I'll just put it to the other side. Equals H max rho G. H max rho G. So what is this? H max 40 over R rho G. You can write this as 2T over R rho G, right? Times 2 equals H max. What is this? 2T over R rho G. Remember that is H, right? When the bottom layer is flat, it is H. So by this, you can say when the bottom surface is hemispherical, also hemispherical, you can fill twice the liquid height, right? So that is going to be H max. They might ask this in like MCQs, right? So H max is equal to 2H. They might ask this in MCQs, okay? So if you know that without wasting time, you can just get it. Okay. So you can write H max is equal to 2 times what? 2 times liquid column height when bottom is flat. Get it? Take it down.